So you'll set up a set of instructions, right? And like then tell your computer like do this, call this, or do that, right? But it would be pretty inconvenient if everything you want to do every time you had to reload into memory more than once instead of accessing. Instead of being able to access it just wherever it is, right? So let's get the Spotify example. One sec. All right, yeah. So in a similar way to how like when you have Spotify somewhere in your computer, right? And then like if you want to access it, then you have like its address stored somewhere, right? And then you can go and access it. We do a similar thing when writing our programs. So how gonna put this? We can in our memory, right? Here's an example right here on the right. You can save little, so like in a similar way to like how you save functions or like Spotify programs, right? Like how you save I guess this one's not a good example, but so remember how in another examples we've done, so like outside of int main, we do something like int make 12, right? And then we make 12. This takes doesn't really matter because yes, does matter. Right, and then we, whatever, we make 12. In a similar way to like how these functions are written out, and then you go through int main and calls it, and it calls it. We can load subroutines, right? Like this is what they're called. We can load subroutines into the memory where into our instruction packet of memory, right? And so we can have this. So think this little subroutine. You can think of like the print beach function. And so this entire block of memory is just it's one piece in our little memory array, right? So we had a bunch of these, and then we've allocated some space to this where right. So we've allocated so like some bit of space where if we go to this address, then we'll just run through what's going on here, right? Again, here, like it's just a little subroutine, like just a little subset of your memory array, where you have a specific function that you can keep coming back to, right? Here, we'll get into reading this more thoroughly thoroughly in a second as we implement it, but you can see here in the comments what's happening is like you're saving an address somewhere and then you're calling. So in register 0, we're storing address 6 and then calling at register 0, meaning we're going to move to whatever is at register 0 right now, which in this case is address 6, and then just run what's going on there. So, right, like this instruction, and well, this one's pretty small, right? Like it's doing save, the call, and then halt. We could add a bunch of more instructions here, right, and just do a bunch of more different things. No matter what's going on here right now at the moment, right? Like this call function, this is they come in pairs. They come with call and return, and so this call here, it'll skip out of the norm. So usually when we're running through, yes, here it is. You're running a program counter, we just like keep incrementing up one by one by one by one by one, right, and keep it in order. Right, this is what we're doing right here on every step, just incrementing our current index by 2 or by 1 or by however much we need to increment it by, right, and just going forward. Now this, right here, this call instruction right here, let's just jump over all of this and then go somewhere else in our code and run that. And so in this case specifically, right, call is jumping to whatever address is stored in register 0. What's stored in register 0? The address we stored just right before it, address 6. And so in our what the contrived example I just wrote out, it jumps over all of this, right? All of these instructions. These could be named execute something else, right? And so all of these would be like different instructions. We'll jump over those and get into this little bit here, right? And then run this. And you see here at the end is the return function, right? So the cool thing about this is like now you have a little piece of your memory where this is stored, and then all you ever need to do is just keep jumping to this when you need it. Again, very, very similar to how outside of main, you can write a bunch of different functions, right? So I don't know, like 120, right? 212, 122. And so, right, as you're running through this function is going line by line, right? Going down by the program counter, just one by one, in a similar way into how, your program counter starts here, and then it starts incrementing one by one. But then it runs into, then we call make 12 here, right? Right. And then, this doesn't keep moving down. It'll like break out of the, this is going down, 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 down. And then when it gets to here, it breaks and it goes all the way. Oh, crap. Here we go. Let's make this one 12. And it goes here, right? And then it runs whatever it needs to run here. And then once it's done, it returns, right? Let me show you. Let's do it right here. We'll get rid of all of these. And so, yeah. So we're running down our functions, right? The same way we're running down here. And then when we get to this call, right? Like this call right here, right? We're going down. Instead of it keeping going down and then halting and stopping a program at all in this particular case, it jumps over to somewhere else where the subroutine is saved, right? Like think of all of these guys, they're subroutines. So yeah, it's pretty much this is what subroutines are, like little pieces of your memory where you've stored just a specific set of instructions that you can call on later on, and like you can see this is like what they're called, right? Like we're calling them like call and return, right? So call, so you can call some function that you've defined, some subroutine that you've defined somewhere else in your memory, and then return, so that you can return back to the flow of the program you're running, right? The original program flow where we're going up the PC counter. So let's try and implement one. All right, let's try and implement these. So let's get rid of all of these. right, call and return. So we're going to be able to get rid of this in a second. So let's go to the drawings here. Let's get rid of you. All right, and so again, this is our program. We could call it whatever we want. We could give call and ret whatever numbers we want. For the sake of making this easier, because we already have it, we can see here that call is 10. So we just turn this into 10. And 11 is ret. So we'll just call this one 11. All right. And so we've defined those. Oh, here you guys are. There you go. I'll keep you out of the way. All right. And so now we can get rid of this. Okay, so we've added two new functions, right? We have call and ret. Let me just get to this part of the code, make sure I'm not going to miss anything. All right, and so we've got our call and ret. Now let's add the switch cases. See how those work. So right after pop, save. We've got case call, right? And then case ret. All right. Now let's start with yeah, let's definitely start with call. Because it's going to be harder to figure out if we don't have call. All right, so let's try and figure this out together. So the first thing we want to do with call is here. So we know that when we're getting call, we're getting just one argument passed in with call. Again, like one parameter that's being passed later after it. So and what we're getting is the number of a register, right? So like, oh wait a second, do we have save here already? Okay, yes. All right, so first off, in this instruction set, we've saved the value 6 into register 0, right? So if we had our little set of registers, 3, 4, 5, 6, 7, 8. Right, so right now at register 0, we've saved 6, right? Save 6 and register 0. It's just what we're doing with save, right? Our value is the first one as the first argument. This is 6. Our register number is 0 as we're going to save it. So it registers at reg number. We save that value. All right. So all right. So the first thing we want to know is where are we going to go back to when we're done with call, right? Once we finished calling whatever is at this address, right? This register 0, which in this case now is line 6. We want to know where to return to, right? So where do we want to return to? Connor, do you have a clue?
I always talk when I'm muted. Yeah, I'm a little lost at this point. I was actually opening up the repo to kind of get an understanding more of what's happening.
All right, no worries. Walk through it. So we're gonna call our call function, right? And then we're gonna jump somewhere else over in the code, right? In this particular case, we're gonna jump into what's a register 0. So what's a register 0 is address 6, but this is breaking us out of the loop, right? And so let's see, we were following our normal line down here, and then boom, now we have a break. And so like if we didn't have this break, we would just keep going straight down, right? Like all the way here to halt. But that's not what's happening. That's not what's happening right now. What's happening right now is we're breaking somewhere out and going to a new instruction set, right? And so after we're done with all these, and like you'll see here, right, this subroutine itself is calling somewhere else. So this is gonna, go down somewhere else, and this is like it's gonna get crazy, and it's gonna happen. It's gonna happen a bunch of times. Kind of like when you're doing recursive functions in Python tutor. You guys remember how it'll build like one block and tell you, all right, I have some values here, and this is what I want to do, but then another function opens, right, and there's a bunch of these little squares. But it's always keeping track of this first one, right? This first one always tells you where to go back to. So the similar way here, right? We're starting here, and then we're breaking, we're going all over the place. But we before we go all over the place and have no idea where to return, we need to tell return where to return to. So where we want to go to is just like after we're done with all of these, we just want to keep going to our next instruction. So how would we save this here in our call case? It might be a little bit more straightforward than I'm making it seem.
We would go back to I think it might be the program counter. I think one of the pointers or one of the counters is jumping to a new location. So we'd have to just store where we came from and then just go back to it. Is that possibly correct?
Program counter or the stack pointer?
One of the two. I think.
I say the program counter.
Yep.
Yeah, I would say the program counter because the stack is not for subroutines, from my understanding. But
yes, stack is what we call the stack. When we have the stack pointer is where we're storing our variables or local variables. Our program counter is what's telling us what instructions to run. So yes, we are moving our program counter right now. But you were close, Brian. You were close. So. Return address, right? Like this is just literally telling us like storing in a variable where we're gonna go to after we're done, after everything that happens. Like we make this call function and we open up Pandora's box, right? Like this is going like it's normal flow call, and then we get call and it starts going somewhere else, right? And it's just like crazy stuff that's going on. We don't even know what's happening, but after all of this is done happening, right? Like where is this? Where do we want this to go back to? Right? Like where do we want the program counter, right? The program counter is gonna start going all over the place, but then we want to get it back.
The area right after where we were, the area after the line of the.
Yep. If we set it to the same place, yeah, we would just get stuck in an infinite loop and be calling itself over and over again. So we want to move on to the next instruction. So what could this be?
PC plus 1.
All right. Yes.
Maybe.
Just plus 2 because we do have an argument.
Oh, okay.
Right. But yes, that's right. And then so yes, in your guys' program, it will probably look like PC. In ours, it's called current index. Just the way we wrote the emulator. All right. All right. And so now the thing is, we need to store this somewhere. So we have this now in our local variable, but like nobody else has access to it. Like no other function, no other program. Where can we store this so that we can access it later on when we need it?
In a register. Maybe.
Almost. Yeah, that's a good idea. I'm not entirely sure why not the registers and actually the stack, but yes, we'll store it in the stack. I honestly don't know why not in the registers. Now that you pointed out.
Finite
In
amount of them.
in RAM?
Sorry?
In RAM?
Yes, in RAM and memory, just like in our so
We write it into RAM, so maybe we can use the CPU RAM write function.
so stack is in your RAM, right? So yes, it is when we say stack, like it implies you're doing it into RAM. One good reason. Go ahead.
No, go ahead. I'll ask after.
So I guess this is a good time to show this. So I guess yes. Why the stack and not the registers?
Because this stack is dynamic, and the registers. So it'll go away. You're leaving that place eventually. So eventually you're just using it for the subroutine for a second, and then you're not using it anymore. So
right, you're gonna
yeah.
You want to get rid eventually, and then you can stack these one on top of each other. So
this feels kind of like the interrupt thing, where like if you're going to service another thing like a subroutine or whatever, you want to take any relevant stuff from the original instructions and like store it over in RAM. That way, if the subroutine needs to take advantage of all your registers, then you don't have to worry about losing data.
Yep, that was so great.
Copy stuff back in is needed when it's done.
We very intentionally won't be getting into interrupt this week, but yes, what you said about going into different parts of the program and keeping the registers open for any other subroutines to use, is very true. And so another reason. So again, this is not super intuitive, and it's like I just told you, starting to make sense for me now, right? But as you're popping, so you're gonna call this subroutine, and then this other subroutine is gonna get called, right? And so other subroutines might be getting called, and so let's see. So we have our first function, right? I think going back to like the recursive kind of analogy, and so you're keeping right in the stack, in the call stack, right? You're starting to push the parameters and the return addresses of what you want, right? This is right. By the way, when you call a subroutine and you get these parameters, the return address, and whatever local variables you're declaring, right, like inside the subroutine, these get pushed into the stack. And so as they get pushed, right? Here's a great example. Right. Every procedure will start pushing each of its variables and its arguments onto the stack. And so because procedures 1 is calling procedure 2 and 3 and 4 in that order, let's go back to the code so we can make this drawing. As we're pushing those into the stack, right? So whichever one is being called last is going to get worked with first. So we bring the program. So we bring the program all the way down here, right? This, let's say, EF is directly related to this last call we had right here, and so it just in the way the data structures work, right? Like whatever gets pushed last, last in, first out, okay? like with the dishes. When you have it with the stack, you can just call these subroutines, and then as you're done, just keep pushing them up. Not the same way we use registers. Registers are more static stuff, the right word, but we keep them there. Just like to be accessed, whatever. So a little bit of a rant there, but say yes, register is a very good way to think about it. Just stack is a lot more useful for us to use when storing these variables. So when storing the return address for program counters specifically. All right, and so well, literally what we'll do is then we'll grab our program counter. Where are we keeping our program counter? Does anybody remember? We'll decrement it. I'm missing a number here. Anybody tell me what that is?
Register 7.
Yep, that's right. That's just the one we said. Where is it? Just up here, right? Size of memory divided by size of memory. We had that chat yesterday with Zach. Right, again, like the benefits that we want from the register is not the stack, right? We just have that variable there, and we know that that one's that, and no like moving around with stack pointers or whatever. Just this is registers. This is where it's at. So in our return address, we're on our stack, and right, like just like how you're seeing here, like in our stack as we're loading stuff in our stack, our stack is this bit right here. We're gonna store our return address, and so memory. So we've decremented our stack counter. So if it started 128, then we're moving it down and then storing it there, right? So register 7, like we are just pointed out today. I was making the mistake, pushing it down, right? Pushing it down first, and then in there setting the return address. Okay. Right. So again, think about this. We're in our registers. So we start at register 0. We store the address. Then we call the register, and then once we call the register, we want to have somewhere to return to. Like we want to know where to return. It's going to be a little bit more obvious in a second when we implement ret, how this is going to work with the counter, but just know that. I guess we can write it now. Pop the PC of the stack. Right, and so why pop the PC of the stack? Because we're storing it in the stack, right? Like in our why PC and not SP? Because in our SP, we're using our SP to store our program counter, right? And so as we're calling more subroutines, we'll keep pushing the stack pointer down, right? And then here, and then here, and then here. And as we're done with, as we get done with this, with any subroutines, we'll return, and that'll start pushing us back, right? We'll be popping off until we get back to our original program counter, which is, again, this is going to be return address, right? The one we stored, the one we're storing right here. And so as we're moving down, making more calls to more subroutines, right? And like storing their variables, storing everything in the stack, right? Just like how you see here, right? As it's calling, you're storing the parameters, the return addresses, and then once you're done, since you already have access to that, since you've been storing the return addresses, once you're done, you can know to this is like return address, which we set to current index +1, current index, or what is it, CPU PC. So like this instead, right? It'll just we'll have in our stack stored where we want to go next. So this is just what we're doing right here, right? Like setting a return address to where we want to go after we're done with like this. Like we open this Pandora's box first, but then when we're done with this Pandora's box, we want to know where to go to next. And so we're storing that here, like decrement our counter first so we can push, and then just like storing the value, right? Storing that value here. All right. All right. So we've taken care of our return value right now. So now we want to go to that address in subroutine, right? So like, okay, we've stored what we need to store, but now we actually want to get there. Anybody, I guess, Hargo, how would we go about that?
Doing what again?
So so we want to basically move our program counter, right, to whatever is stored at the register we're calling. This case is register 0, but we want to move our program counter from this instruction over to this instruction.
Okay, right. So this would be where we actually move the program counter to the new like area that we're gonna execute.
Yes. So far we've just want to go back to. So we do that first, and now move the program counter to the specified sub to the address of the subroutine, right?
Okay.
How do we do that?
So we'd set current index to current index plus, or just like in memory current index plus 1.
Memory current index plus 1. So what's
I was looking at the spec, and the call instruction takes in, I guess, right, it takes in, calls a subroutine function at the address stored in the register. Okay, so we want to access a register.
all right. So where should I write this?
So what's stored in memory, current index plus 1, register that we want to access. So instead of current index, we'd write like register number, and then we'd access current index plus 1 from memory, and then we would set current index to like whatever a register number is, like the register in register number.
So sorry again. So current index, set this to what?
Yeah. So registers, and then we'd access the register number.
All right. Awesome. That's perfect, right? So register number, like this is what it's telling us, right? Like we're the number we're gonna get after our call is gonna be the index of our register. So right. So like memory current index. So memory current index is this right now. Memory current index plus 1 is this 0. And so we want to store that value, because this value could be whatever, right? It could be 7. I mean, anything from 0 to 7, right? Because we've got 8 spots in a register. We just decided that this would be 0. We could call this 3 and 3 for all we care. It would work the same. But we just want to make sure that like we get to choose whatever we want to store in the register. And so we're storing that number here from memory, and then setting our program counter to whatever value we store there. In this case, 6. Okay, and that's it. Like now we've changed our current index, and so current index when we started was 1, 2, 3, 4. And so instead of it keeping moving forward, now we just instead of usually we increment it by 2, right? This is kind of what we're doing here, but now we just set it to like whatever address was stored in our register number, all right? So that'll take us there, and then we'll do some more calls. And so all right, now we need to return. right? So now we want to get back to where we were. So how do we do that? And this should be a lot more straightforward. Should I call in someone, or does anyone will volunteer how we would do this?
Wouldn't you just like set current index back to the address stored in
Where?
memory register 7? So memory bracket registers bracket 7. Yeah.
Missing an S. All right. Perfect. And then we wanna increment this, so we're done with our push. Is this making sense for everyone? Is this sensical, or is there something look weird about what we're doing? Is it not entirely clear why we're using register 7?
Yeah, I'm not sure why we use register 7.
So remember where we stored our return address in our call function?
Yeah.
Right here?
Uh-huh.
So once we're done with all of these subroutines and doing all of these weird things, we want to set our program counter back to the address we stored. Like that's what we saved it for, so we could go back to it. And so we just need to access where we saved it. And where we saved it is, I mean, there might be more stuff going on with your stack pointer, right, like moving up and down. But if you're following the right procedures, then once you've stacked this off, so let's see. Let's check this out. So in our video here, right, as it's, right. So again, keeping your program tidy, right? So you've been accessing all the variables. We've kept return addresses all along the way, right? 1, 2. Return address of P3. Where is this untitled, right? Right. We've been keeping those return addresses every time we make a call, and they've been added like in a last in first out fashion to the top of the stack. And so as we've been doing so, we've been decrementing our registers array, right? And so as we do that, part of what you have to do with the functions, we're not going to see it that straightforward, because I don't think we do any stack pointer movement in our subroutines in this specific program. But you'd be getting rid of all the variables and then get back to that return address, and you get to that return address with the stack pointer you set here. And so if your stack pointer is kept in the right track, I mean, obviously, right, if something falls out of place, then the program breaks and nothing goes the way it should. But barring those mistakes, we've stored in our stack pointer. Sorry, using our stack pointer, we've stored our return address somewhere in memory, and then as we're pushing back, right. So when we let's do this one again. So, right, this is what it looks like right now, right? This is our SP, and so if we want to move it down, we okay. Wait, this might be smarter. Hold on a second. Just keep this here for a second. All right. And I'll bring you over here. So stack pointer is right here, right now. Stack pointer is also memory register 7. That just happens to be where we chose to store our stack pointer, right? Again, just a little refresher. This one right here, right? 128. This is just register 7 is our stack pointer. Get back to where's call. Here's call, right? And so, all right. So we're setting our return address to current index plus 2, right? So this is right here. Right? We're setting to the current index. Please see, plus 2. And then decrementing the registers. So we're saving it just like in some variable, right? So let's actually let's give it here so you guys can see it. Right, so this is just us saving it in our return variable, right? And then decrementing the stack pointer, meaning we're doing a push. If you notice, this is exactly what you do on push, right? Push register 7 memory registers and set that to vol. Exact same thing here, right? Getting a value, decrementing the pointer. So decrementing the pointer, moving it down. And then setting memory at registers to that return address. And so, right, so this is our return address. So we'll do array instead of program counter. Right, so good so far? All good so far? All right, and then here in ret, simply what we're doing is just doing the opposite, right? So like current index, so then our program counter used to be 00. Now we set our current index, in this case, an index as well. So once we saved our spot, this is what we just did right now, these 3 steps. This is this part. Now we're moving that PC, right? We're setting this to, you know, whatever value was stored there. So it'll go somewhere else, somewhere crazy. Let's, I guess 47. Might be doing this wrong now since this is hex, but just please excuse me. I don't want to make the calculations right now. Actually, what is it? Day 16, whatever. No, that's sorry. I'm not gonna waste your time. Actually, just did it. Right. And so this is where we're setting our program counter to right now. Right. And so this is going to do a bunch of crazy stuff, right? Like this is where the subroutine is, just like some other random address, right? Like I'm coming up with an address. The number itself doesn't really matter. But this is what we're doing, right? Setting current index to whatever number we stored in registers. And now, okay, so now we've done that. Now we want to bring this back to where it was supposed to go, right? Like we stopped it here. Say we stopped it here at 2, right? This is where we left off. Now we want to make sure we get back to 3. Right, this is what we stored in our registered address, right? Like this pair of letters right here points to, let's say this is where we left off, right? So arrow pointing out, and then arrow pointing in. This is where we want to go back to. And so all we're doing now to set the PC, like instead of it being this here over somewhere crazy, we're just grabbing current index and then looking for in memory what we stored as our return address. And so in order for us to, again, sorry, let me rephrase. So now that we're returning, right? Now we're done with our subroutine, and then here's the return. We want to go back to where we were supposed to go next. In this case, like right here. And where do we store this address? We stored it here on the stack. And so that's why we're accessing that here on memory register 7, because our stack pointer is still pointing, right, at like the last place where we pushed our return address. Is that, did I help clear that up, or did I make that more confusing?
I think it's cleared up, but let me think about it for a minute longer here. I'm still trying to wrap my head around it, I guess.
All right. Yes. I'll try and explain it one more time, maybe a little bit more simple, but we can come back to this question after the break. We're doing our call. We need somewhere to go back to, right? we want to go back somewhere, and so we have a return address, and so that return address we store in our stack. And so in order for us to get that return address back, we just call it from the stack, right? We just pop it off. Notice how this red here, right, getting current index from stock and then incrementing the pointer again is very similar to pop, right? Just like getting what you want from the stack pointer and then just incrementing the stack pointer again. This is just we stored our return address in the stack pointer, right, in memory register 7, and so now we want to get that return address back, so we call it from our stack pointer, which is memory register 7.
Okay, I think I see. Yeah. Okay.
Yeah, I might have delved a little bit too deep into the details, but this is in simple high terms. We're storing at a stack pointer, so we just get it back from the stack pointer. This is, if you notice, right, like return address is what we want, and we set return address to memory register 7. We don't have access to return address now as a variable because that was somewhere else in another function, but we did store return address in memory register 7, right? Just what you see here. So we just get it back from memory register 7. That's it.
Luisan, just to clarify, we're getting that address and then we're moving the stack pointer, but the one that was kind of above it, it's still there, right? We just moved it, got our value, moved our pointer, but it's still at the previous spot where it was, right? We just can use it now again if we want to move up and override that.
Which you're talking about the previous value here, or if we move?
Yeah.
This?
Yeah, because when we after when we're doing the pop and we get the current index off of that off of memory from memory register 7, and then we move our pointer down one, we do register 7 plus plus. The previous one, that current index is still there. We just don't care about it anymore, right?
You mean this one, or you mean this one? RA or 03? Which one are you referring to?
03, I guess, or 02 if we were there before, and then we moved our stack pointer down one.
Those are all still there, right? So
okay. Yeah.
If we were doing it in an array, it would have looked like this, right? Array. So like we still have access to everything that's before the stack, right? Because we haven't popped it off. Like it's the bottom plate, right? And so as we're moving back, like in a similar way to when you do pop, you just get rid of this one. But now you're pointing, or I guess this was 3, right? And again, sorry. So here's the array. And as you're moving back, you're forgetting about this one. You're not deleting it. You're not setting to 0. You're just forgetting about it because it's now on a stack pointer. But now you're back to the next item you want to pop. If we lost access to everything that was before this, then there'd be no sense in having the stack, because then you'd only have access to like one value, and then that's just storing a variable. That's not keeping a stack.
Okay, yeah, I think that clarifies it. Cool, thank you.
Yeah. Think about it like this image right here, right? You're like moving stuff up here, and then we didn't lose access to where we want to return from those variables, right? I don't want to draw the squares again because it takes a while, all of them, but right, remember these function return squares, like these are set up in a stack, and you have to like keep track of where you want to go back to. Here's just another way to see this. All right, and so all right, now we've done a lot of talking and a lot of let me just clear this up. All right, so let's save this. Let's where is this? 137. Where do
Don't we need to save something there first?
do what? Sorry.
Don't we need to save something before we can call it?
Yes. But that's set in the instruction set here in call.meta. Or how do you ask?
Because we didn't do that part yet. So that's why.
Which part, the save?
Yeah. Or did I miss that?
I thought we did it this week, but I might have missed it. Anyway, save, I'll show you real quick, but just what it does is it'll save some value into a register, right? So in register 0, right, save value 6.
So is save basically LDI then?
Say, oh yes, yes, my bad. Save is basically LDI. I forgot to tell you guys this. We refactor this. If you notice, we don't have PRN and some of the other functions we had yesterday. All we have is this is reordered again. Yes, save is LDI. Think about it like this.
That doesn't help me that much.
So remember the case LDI we had yesterday, and then we used that. Remember this one?
Yes.
All right. Is it clear now?
Yeah, I thought we were talking about something else for some reason.
All right, no worries. Let's see. All right, finally. All right, and so now just before we run this, notice one thing, right? So we're gonna print Luisan. I also added before the class started, I added myself here. So we're gonna print Luisan instead of Beej. Notice how if this would run like a normal program, you'd expect to have Beej run first and then Luisan. But let's see what happens. Right? Luisan actually gets printed out first, even though it's later down the line in like the linear fashion of the program. But then Beej gets printed. And let's have a look at the instructions to see why. Right? So going on here, setting our subroutine address, we're calling register 0. So add register 0 moves us here, right, to address 6. And so in address 6, before we get to printing Beej, we're saving another address, right, address 14, and then calling that, right? So before we even get to print Beej, we move from here. We move from this, before we get to print Beej, this call subroutine takes us to this subroutine. And then here we print Luisan out. And that's why you see Luisan being printed out first. And then once Luisan's being printed out, we get return value. And then, all those fun things we did with call and return, right? This call saved its return address as the first print Beej. So once we're done with print Luisan, this return is going to return back to print Beej here. And then once this is done, right, like this original call saved its return address to here. And so once this is done, then this goes back to this address, and then the program stops and we're done. All right. That was a little long, right? Like a little bit of an hour, but any questions before we head out to lunch?
So is this how you can have your emulator computer then run programs that are in different spots of memory rather than just in one linear fashion, how we've been doing it so far?
Yeah. And so, I mean, that'll, again, depend on the, like in this emulator, is going to depend on the file you're running. But think about it like, so, like if we were writing out this one ourselves in C syntax, it would look something like, int. I'm gonna butcher it up in syntax just to make it quick, but right. So like int main is here, but then we have void print Beej function here somewhere else in our memory, and then below that is print Luisan, right? Like these are not stored sequentially. These are written down in like different spots in memory. But then what you're doing is, print Luisan, right? Part of print Beej is, call print Luisan, right? And so right? And so again, it's what you're seeing right here, right? So starts out. I mean, we're missing. I'm doing this to be quick. I'm not going through all the details, but the main function is what runs, right? And then this main function is gonna call, like we would have expected to, run an order, right? Just go down this line. But then you're doing this call, and then this call is bringing you all the way over here, right? Like kind of like how this is doing, it's bringing you to address 6. And this is stored, like this is not stored sequentially, right? Like this is, we don't store that here for it to keep going linearly, right? We didn't write it out. We just like saved it somewhere else so we could call it more times. And so when you're calling print beach, you're moving your program counter. It's not going to keep moving down the line. It's going to move somewhere else in how you in the program you wrote. Run this, right? Like this particular one is telling you to call some other function somewhere else in the code, all right? And so it just happens to be down below. And then once it's done, it's just coming back, and then finishing its in its usual fashion. All right, cool. Any other questions before I let you go for lunch? All right, cool. Yeah, I'm noticing.
Kind of one. We're not doing a heap. We're not doing heap, right?
No.
Like okay.
No heap.
Right. We're going for lunch already. Are we discussing the questions?
So however you guys want. This is a 5-minute break. After the 5-minute break, we'll do interview questions if you guys want to hang around and go over those. If you don't, you're free to go to lunch. This is going to be recorded anyway, so you can check them out. Or the questions are there, so you can like research them on whatever you want. We're going to have a short session after the 5-minute break. So up to you guys. All right. So I'll see you back here in Hive. Any requests for how you want to be called back today? Since we've been mixing it up.
Always a fan of Kiwi hours.
Oh, by the way, let me stop recording before.